Hello everyone, welcome to the video about type 1 and type 2 errors, power of a statistical analysis. So what are the type 1 and type 2 errors we talk so much about in statistics, and what is the power of a statistical analysis, the sample size you should need in order for your statistical test or analysis to be reliable. So type 1 error and type 2 error. First of all, after any statistical analysis, we decide if we should reject or not the null hypothesis. These are always two decisions possible, rejecting the null hypothesis or retaining the null hypothesis. But there's always a risk in taking any decision in statistical test, as well as in everyday life decision actually. For whatever decision you have always a risk of getting mistaken, okay? So let's say we live in a binary world. So we have either we do not do or we do, okay? Rejecting H0 when it is actually true. So imagine you conclude that a patient has a cancer and in fact he doesn't have any cancer, he's perfectly healthy. You would commit a type 1 error, for example, here, okay? Not rejecting H0 when it is actually false. So concluding of no disease when there is actually a disease, in that case you would commit a type 2 error, okay? So for whatever decision you take, there is always a risk of making an error, okay? Of making a mistake. So if you reject H0 and it's actually true, it's a type 1 error. And if you do not reject H0 and whereas it is actually false, it's a type 2 error, okay? So now I want you to think in everyday life when you're doing a decision, you might be wrong in taking that decision. For example, you might want to watch a movie at the cinema, and in fact the movie was completely rubbish and you have wasted your time, okay? In that case, you would have committed an error. So it's either type 1 or type 2, following what you decide for what H0 is, but there's always a risk of getting mistaken. So in this example, for example, where a medical team wants to determine if a patient has a cancer or not, H0, the patient has no cancer. HA, the patient has cancer. Okay, this is how we deal at the moment. Okay, remember H0 is when there is when this is neutral. Okay, when nothing happens, the patient is healthy, comes to the clinic, but they didn't see any cancer. So there's always a risk in taking either of these decisions, as I just said. So rejecting H0 when it's actually true, type 1 error. Retaining H0 when it's actually false, type 2 error. Increasing your risk of making one type of error, so let's say you are okay with the type 1 error, decreases the risk of making the other type of error. For example, if you conclude that all the patients coming who are coming to the clinic have a cancer, you will make a lot of type 1 errors because you will have concluded that all the patients have a cancer, whereas a lot of them do not have cancer. So that is good in some sense because people who really have cancer are taken care of. But for many people who did not have cancer, they have been diagnosed as having a cancer. And what is bad here is that because you have to increase the number of treatments and beds for people who did not need it, you are wasting time and money. So you could conclude that indeed everybody coming to the clinic have a cancer, but you will have committed sometimes the type 1 error a bit too much, if you know what I mean. And in terms of cost for the clinic, the number of treatments and beds available, it's important to try to decrease also that type 1 error, okay? I agree that if you had committed the type 2 error, you would have probably be more inclined of you would have maybe put some people into danger of death because you would have concluded that most of the people do not have cancer and some of them had cancer, so they needed treatments. But you see that in that case, it is better to do more type 1 errors than type 2 errors. But in some other cases, it is better to do type 2 errors than type 1 errors, okay? So it depends. First of all, you have to define what the null hypothesis is and what the alternative hypothesis is, first of all, okay? Then after that, you have the type 1 error or the type 2 error, okay? So the maximum risks allowed, what are they? The risk alpha that we called the significance level. It is the maximum risk we are willing to take to commit a type 1 error. For example, rejecting H0 when it is actually true. It's not an example, sorry. Rejecting H0 when it is actually true. Okay? So that's the type 1 error, but alpha is the maximum risk you are willing to take to commit a type 1 error. That maximum risk is 5% usually. Usually, your chance of committing a type 1 error, like the p-value, basically, your probability of making the type 1 error, which is the p-value, must be less than 5%. Okay? So the risk beta, on the other hand, is the opposite. It's the maximum risk we are willing to take to commit a type 2 error, retaining H0 when it is actually wrong, when it's actually false. Patient has a cancer, but the doctors concluded that he was healthy. Usually, beta is equal to 20%. Because the power of the statistical analysis, you must have heard of the number 80% of power achievement. The power is 1 minus beta. It is 1 minus the maximum risk we are willing to take to commit a type 2 error. The power of a statistical analysis must be higher than 80%. If the maximum risk to commit a type 2 error is less than 20%, the power needs to be more than 80%. The power, it is the ability, or let's say the chance we want for our analysis to detect a cancer when there is actually one. Okay? We want the power to be 80% usually. So the link with the p-value, okay, as I said, in statistics, we reject the null hypothesis H0 when the p-value is lower than alpha. The p-value, which is the probability of rejecting H0 by mistake, rejecting H0 incorrectly, is the type 1 error. And if that p-value gets smaller and smaller, the probability of concluding a cancer incorrectly is small, of making a type 1 error is small, so you conclude of a cancer, okay? P-value low means H0 must go. P-value low, you take a small risk to reject H0 by mistake. So go for it, reject H0. Okay? That risk, so the p-value, needs to be smaller than the maximum risk allowed for making the type 1 error that is called alpha. Okay? The power now. Let's go back to the power. So beta is the maximum risk we are willing to take to commit a type 2 error, okay? To not reject H0 when it is actually false. So that's the type 2 error. The probability of making that type 2 error is the probability of making that type 2 error. Beta is the maximum risk you are willing to take to commit, the maximum probability allowed, the maximum chance allowed to take, like to not reject H0 when it is actually false. Sorry. Power is the chance of detecting an effect when there is in real life an effect in the population. So let's go back to a model, well, a hypothesis where H0 is no effect and HA is effect. So that would be the probability of detecting an effect. So imagine in the population there is such an effect. The power would be the probability for your test to detect that effect. Okay? So let's say we have a microscope that has a lot of power if it can detect 2 cells. Okay, let's say you have the first square here. You do not see 2 cells here. You just see 1 cell. So in fact, there are 2 cells. Imagine that there are 2 cells. Well, in that case, this is the case. Your microscope in that case would not be powerful enough to detect that there are 2 cells. If you look at the square on the left, it's not possible really to detect 2 cells unless you get very close to it. If your microscope only detects 1 cell and in reality there are 2 cells, then it lacks of power. So if you zoom it a bit, then your microscope becomes more powerful. In the case where you really have 2 cells, you will be able to detect them with the powerful microscope on the left. On the right, sorry, on the right, okay? In the case where there would not have been 2 cells, well, the powerful microscope would not have detected anything, okay? The power behind it, you have to imagine that in the population, there is the effect, so we assume that there is the effect, and then what would be
the ability of your test, of your microscope to detect two cells if in case there were two cells here, okay? There might be not two cells, okay? It's just imagine that there are indeed two cells. What could your microscope see? If it can see these two cells, then that's fine, okay? But it doesn't mean that in real life there are two cells, okay? It's imagine there are two cells in the box. Will my microscope be powerful enough to see these two cells? That's the question, okay? If so, yes. If not, no, okay? And in a statistical analysis, it is the same. Your sample will have a lot of power if you can detect a difference between two populations when there is actually one, okay? But when there is no difference, we don't care. There is still a power, okay? There is still a power. It's just in the power calculation, we imagine that there is a difference between two populations. What is the probability of detecting that difference with 20 people in each group? What is the probability of detecting that difference with 100 people in each group? So if you increase the sample size for each group, you will increase the information about the population. So you will increase the information about the population. And so if there is indeed a difference in the population, indeed, in reality, actually a difference of 5 centimeters between men and women in the population in terms of height, if you take 100 men and 100 women, you would have more power, more ability to detect that difference than if you had taken 5 men and 5 women, okay? Because if you increase the sample size, you are closer to the reality. Okay, so if in the reality there is a difference between the two populations, you will be able to detect that difference. Okay, but it doesn't mean that in reality, there is a difference. Okay, it's if in reality there is this difference, if in reality there are two cells in the microscope, you would be able to detect it with your analysis. You would be able to detect it with your microscope, okay? It would be a powerful microscope. It would be a powerful analysis, okay? So by increasing the sample size, so in the case of the microscope, increasing the zoom, let's say, you will be more and more able to detect a difference if there is such a difference in reality, okay? And it's not just detecting a difference, it's if there is a difference in reality. So please, I repeat, like 10 times this, because this is really important, because in some books, they just stop at to detect a difference, but that's not true. It's to detect a difference if there is such a difference, if there is such an effect in the population in reality, okay? So the thing here that is a bit hard maybe is that you need to define an effect size. So when you conclude no difference between men and women in terms of height, the alternative hypothesis, so when you're not in the world of H0, it is there is a difference, okay, between men and women. But there can be a difference of 2 centimeters. There can be a difference of 2 nanometers, of 20 centimeters. It depends. What is the practical difference you would like to detect if such a practical difference existed? Okay, that's the question. And that's why in computing power, it all depends on the effect size you need to decide, basically. You can cheat and have a very good power if you put an effect size of 30 centimeters, because if there is indeed a difference of 30 centimeters between men and women, if there was indeed a difference of 30 centimeters between men and women, you would just take 3 women, 3 men, and you would indeed start to detect that difference if such a difference existed. So you can see that if the effect size is bigger and bigger, then the power will be big with a small group, with small samples. You would be satisfied, basically, with your statistical analysis with just 3 men and 3 women. If you want to detect a difference of 30 centimeters, if there is indeed a difference of 30 centimeters. So this effect size, this difference between the groups, is a practical effect, okay, for your company, for what you are researching. If you would like to detect a difference of $200 between that salary, like the salary from sector 1 with the salary from sector 2, if you wish to detect such a difference,
what would be your chance of detecting that difference with just 3 employees in each group? Maybe it might not be enough to conclude that there is a difference of $100 of salary between the two sectors. Okay? So between the two populations, men and women, if the difference is very big, let's go back to that, then you have more chance to detect this difference from your samples than if the difference in reality is small. So if the difference is just 2 centimeters in reality between men and women, then you would need to take maybe 300 men and 300 women in order to compute their means in order to detect a difference of 2 centimeters at least. Okay, so you have more chance, then you have more power, then the power is bigger with a big effect size. Or you have less chance, you have less power, the power is smaller with a smaller effect size. Okay, so it's that if in reality there is a difference of 15 centimeters, you just need probably 4 men and 4 women. You would be satisfied with this test if because your power would be good, the probability of detecting 15 centimeters of difference, if that was really the case in reality, you would just need 4 men and 4 women probably to detect 15 centimeters of difference. Okay, if they were different of 15 centimeters. If in reality in the world, in the population, the difference between men and women in height was just 2 centimeters, you would need more than just 4 men and 4 women. Okay, you need more information to increase in order to be to meet the fact that it is 2 centimeters. Okay, but in the reality, like that we know, we don't know if there is a difference of 2 centimeters or 15 centimeters. It's just in the computation of the power. Behind the computation of the power, we are in the universe where there is indeed a difference of 2 centimeters. What is the probability of detecting that difference of 2 centimeters with 5 guys and 5 women? Okay, it's probably going to be small, maybe 15% would be the probability. You need at least 80%, okay, of power. So as I just said, you might be satisfied with 3 or 4 observations if you want to detect, for example, a difference of 50 centimeters between population M and population F, if there was indeed a difference of 50 centimeters. 500 observations per group at least would be maybe needed if you wanted to detect a difference of 1.5 centimeters. If you wanted your probability of detecting that difference to be more than 80%. The satisfaction about your sample size depends a lot on the effect size, as you can see, okay? So if your supervisor or your boss wants you to have a power of at least 80%, well, you need to think of a practical effect size, okay? If nobody has any clue of the effect sizes, well, you are free to cheat basically and say like, oh, we have a very great power of 99%, but the effect size is 90 centimeters to detect between population M and population F. But we have a great power, so that's fine. My analysis is fine. In reality, it's not really fine because it's not really a practical difference to detect 90 centimeters. When you have a problem with a continuous variable like this, like comparing like a continuous variable such as height, and you can watch my video about the types of variables, the data set and types of variables. When you have no clue of the effect size and you do not want to cheat, because you do not want to cheat really, okay? You, in general, what you do is you take a standard deviation from historical data, like you take 20 people, you take their standard deviation, and the effect size is that standard deviation. I will come back to that when we see the independent t-test in a later video. So I mentioned earlier that the power increases with the sample size. Well, I will repeat it again. If you increase the sample size, like the sample size of the sample of the males and the sample of the females. So if you increase like the number of observations per sample, in that case, you get more information about
the populations, obviously, because you will have had more observations, okay? So if there was an effect in the population, you would be more and more able to detect that effect. So your chance of detecting that effect will go up towards 100%, okay? If you had the entire population, your power would be 100%, okay? Because you have the entire population, you have all the information possible, but that's not possible to have this, okay? I mean, in general, it is not possible, okay? So as a summary, the power is the ability to detect an effect when there is in real life an effect in the population. You need to define an effect size, and if that effect size is very big, you do not need a lot of observations. But if that's very small, well, you need a lot of observations, okay? If there was in reality in the population a difference of 5 centimeters, how many observations minimum would you need per sample in order to observe that difference with a probability of 80%? So in order to have a power of 80%, that's often the question you want to answer, okay? How many men and women per group do I need? If I wanted to detect a practical difference of 5 centimeters, that is, if there was indeed a difference of 5 centimeters between the population of men and women. With 20 people in each group, would I reach a probability of detecting that difference of 80%? That's the question, okay? If that's 70%, then your power would be 70%. And in that case, it's not more than 80%. So there are questions arising. You need probably to increase the number of observations per group, okay? So I want you to remember just to go through all these slides, okay? To digest it well, to practice, and if you have questions, ask me. I have my email in the comments, okay? So now, after this like power type 1 error and type 2 error, I just want to finish by a small slide about the standard deviation in the calculation of power for continuous data. So you do not have to look at it if you are not dealing with continuous data, like in a statistical analysis with continuous data, okay? Such as an independent t-test, okay? Actually, even if you have such a statistical analysis with continuous data, first of all, digest well the slides before this final slide, okay? Because I don't want you to be confused with several notions. It's just that when you have continuous data, when you want to have the power for a one-way ANOVA or an independent t-test, you are often asked a standard deviation, okay? So remember, the standard deviation is what defines the spread in your data. So you have a group of 25 men and you measure their heights. The standard deviation will represent the spread among them. Okay, the mean is the location, the mean is the average between the heights, the 25 heights. The standard deviation represents the spread. Okay, the probability of between the mean minus 2 standard deviation and the mean plus 2 standard deviation, I will come back to that later in my next video, is 95%, usually roughly 95%. So the standard deviation, if it is small, it means that the data is very homogeneous, okay? If you have, so these 25 men who measure 175 centimeters in mean, in average mean, but the standard deviation is just 1 centimeter of the 25 men, then it means that a lot of men are concentrated between 173 centimeters and 177 centimeters. The spread is very small. The data is very, very homogeneous. All the group is concentrated around the mean. That's when the standard deviation is small. And when the standard deviation is small in this data, it means you have more certainty about the population, and therefore the power increases, okay? So you also need sometimes, like for the case of continuous data, in order to compute the power, you need to give a standard deviation if you have nothing. If you don't have any historical data, you give a standard deviation, and you need to find a practical standard deviation, what you think would be the standard deviation in this group. But in general, you have historical data. You can measure some men and women, have their standard deviation, and then put the standard deviation in a power calculation. But I want you to understand that if the standard deviation is small, it means you have more certainty about the population, okay? The standard deviation is big, you have more heterogeneous data in that group. Oh, it means you have less certainty about the population, probably. But we will see that more into details in future videos. I hope you appreciated this video. I hope it clarified a bit some notions. You may not know like everything that I said. You may not retain everything that I have said right now, but please go back to these notions back and forth with your statistical analysis. If you have any question, just ask me by email. My email address is in the comments below the video. Thank you very much, and I wish you a happy day, and hope to see you very soon. Okay? See you.